We've talked about ordinary symmetry, multi-phase symmetry, conjugate symmetry, and we've looked at the cofactor relations, all six of them, and we discovered that all six of them are useful. We can detect them. We know what to do with them. What else could there be? Well, it turns out a lot. We have just scratched the surface. And a lot of the stuff I'm going to be talking about here contains many open problems that are just waiting to be solved. And so let's take a look at some of the other symmetries that can exist. We have strong symmetries, also called weak symmetries in some papers. And other names as well. I don't want to suggest that there's a standard name for this type of symmetry. There isn't. Symmetry group is not just the identity, so it's non-trivial, but the function is neither totally nor partially symmetric. The one sample is AB plus CD. Yes, it has two partial symmetries, but I can also exchange AB with CD. And it possesses a type of symmetry known as dihedral symmetry, which I'll explain further down in the slide. The second example, A prime B plus C prime D, I can exchange AB, the set AB with the set CD, but I can't exchange A and B or C and D. And this is an example of another type of symmetry, another type of strong symmetry. We have an example of partial symmetry at the bottom, AB, C plus D prime. It has one partial symmetry in AB. But of course, we've pretty much covered partial symmetries because everything that we use to detect symmetry can detect either partial or total symmetries. And so that's not really a problem. Now, I need to talk a little bit about permutations and how to express permutations, because that appears in some of the stuff that we're going to be talking about. Let's assume that our base set is 1, 2, 3, 4. We're talking about all permutations on this set. There are 24 of them. All permutations can be expressed as one or more cyclic shifts. And this is the typical way to do it. Now, when I'm programming, we looked at other ways of expressing permutations as just different, the numbers 1, 2, 3, 4 written in some order. We've seen examples of that. That's the easiest way to do things when you're programming. But when you're working by hand, as people did for centuries before we invented computers, it's much easier to deal with permutations by using the fact that they can be expressed as one or more cyclic shifts. A cyclic shift is written as a sequence of numbers in parentheses, which is called a cycle. Here we have a cycle 1, 2, 3, which means replace 2 with 1. So 1 goes to 2. Replace 3 with 2, so 2 goes to 3. And replace 1 with 3. So this is a cyclic shift. And 3 goes to 1 in this. So 1 goes to 2, 2 goes to 3, 3 goes to 1. If the permutation expressed as a cyclic shift only has 2 elements, it's called a transposition. And the second example there, 1, 2, means exchange 1 and 2. That's just a cyclic shift with only 2 elements. It has a special name called a transposition. Now I can take products of cyclic shifts by writing them one after the other, as I have in the third example, 1, 2, 3, 4. That's a single permutation. It means exchange 1 and 2 and simultaneously exchange 3 and 4. The identity element is also a permutation. It obviously is devoid of any sort of shifts, and so I write that as just I. This notation is not universal. We can multiply one permutation by doing one after the other. That's simply the composition of two functions, as I mentioned earlier. Now, a permutation group is any set G of permutations that's closed under multiplication. Now, the fact that it's closed also implies that it must contain the identity element, and it must contain the inverse of every element. So every element that's not the identity has an inverse. Sometimes the inverse is the element itself. Like, for example, the permutation 1, 2 is its own inverse. And here are some examples of permutation groups. The first one is just I and 1, 2. I is in every one, remember. This is an example of a partial symmetry in the first two variables of the function. Now, I also have the following set, I and then 1, 2, 3, 4. If I were to write this a little bit differently, if I were to write it 1, 3, 2, 4, it would be the permutation group of the second example on the previous slide. Let's go take a look at that, or of the second example on the first slide. Okay, so that is the symmetry group of A prime B, C prime D. Again, I'd have to change the 1, 2 to make it 1, 3, and the 3, 4 would be 2, 4. And then it would be the symmetry group of that function. Here is a symmetry group that includes a cyclic shift of 3 variables. You're not going to find any function with this as a symmetry group, but it is a symmetry group nonetheless, and the reasons for not being able to find it are complicated, and I won't go into them. And so I have I, 1, 2, 3, and 1, 3, 2. When I write things in cycle notation, what I'm going to do is, it doesn't really matter what order I write the numbers in. I could write 1, 2, 3, or 2, 3, 1, or 3, 1, 2. But by custom, we put the smallest integer first and then write the rest of it the way it needs to be written. One thing that's nice about the cyclic notation is that we can immediately find the inverse of any permutation. What we do is we write the first element just as it was in the original permutation, and then write the other elements in reverse order. So if I have the permutation 1, 2, 3, its inverse is 1, 3, 2. In the next line, we see 1, 2, 3, 4. Its inverse is 1, 4, 3, 2. Now, this fourth line here has a second permutation at 1, 3, 2, 4. That's the square of the first of the permutation 1, 2, 3, 4, and 1, 4, 3, 2 is the cube. So if I list all powers of a permutation, what I'll end up with is the smallest permutation group containing that permutation. I mentioned dihedral symmetry. This is AB plus CD. And there are functions of any number of inputs that possess dihedral symmetry. It's the symmetry of a blank polygonal coin. The coin is in the shape of an n-sided regular polygon. I can rotate the coin 360 divided by n degrees without changing it. I can flip the coin over without changing it. The function ABCD has the same symmetry as a square coin, with the corners of the square labeled with the variables in the manner shown here. Note that if I rotate the square and do the corresponding changes to the function, it will be the same. You're not going to change it. The symmetry group is known as D8, and part of it is invisible here, and I don't know exactly how to make it visible, but the last permutation is 1, 4, 2, 3. And this is the symmetry group of that. It is known as the dihedral group of order 8. Okay, and it encapsulates all the changes you could make to the square without actually changing it. And it also encapsulates everything that you can do to this function AB plus CD without changing it. Well, there's more permutation groups than that. We have rotational symmetry, which just has, we've looked at this first group already, where it's 1, 2, 3, 4. I'm rotating the elements by 1 position, 2 positions, and 3 positions in that. For functions, no functions possess rotational symmetry if they have fewer than 6 inputs. 6 input functions do have rotational symmetry. For 4 and 5, the dihedral symmetry, or the rotational symmetry, also includes, the function has to include all of the other permutations for dihedral symmetry if it possesses rotational symmetry. We also have Klein symmetry. That's, if I take the 4 elements, the identity element plus all 3 of the permutations that swap 2 pairs of elements, that's a symmetry group, and it's known as the Klein 4 group. It does not exist for 4 input binary functions. But if I let the inputs have non-binary values, say 1, 2, 3, 4, then it does exist. And if there are more than 4 inputs to the function, a subset of 4 inputs can have Klein symmetry. If a symmetry exists, but only for a subset of inputs, we'll call it a subsymmetry. When I first started publishing papers in this area, I tried to say, well, we're going to redefine the term partial symmetry. A word to the wise: if you're doing something where you want to redefine an existing term, don't make up a new term for it, because for some reason people really don't want to have their terms redefined. Okay, and I learned that not as quickly as I should have, but fairly quickly. And so we call it subsymmetry rather than extended partial symmetry, like I wanted to in the first place. Well, how many subgroups are there other than the ones that define partial symmetry and total symmetry? It depends on n. For n equals 4, not many. For n equals 5, n equals 5 is basically n equals 4 with some obvious extensions. However, when you get into n equals 6, there are all sorts of exotic things. There are rotating prisms and of various kinds, and things that are very difficult to define. There are prisms that rotate in opposite directions on either end, which is, of course, impossible in the physical universe, but not in the mathematical universe. Once we get to n equals 8, the number of different symmetries is astounding. So the number of subgroups explodes as n becomes larger. There are some websites on the internet that list the subgroups of S sub n, I think all the way up to S sub 18. And the number is truly astounding. So is strong symmetry important? Yeah, it kind of seems that way. One type of strong symmetry is hierarchical symmetry. Let's go back to this function I've been using over and over again, AB plus CD. This has hierarchical symmetry because I can exchange A with B and C with D, but then I can group A and B together and exchange it with the group CD. Hierarchical symmetry can have many levels. Here's one with 3. The hierarchical symmetry papers have found ISCAS 85 circuits with many levels of hierarchical symmetry. I don't remember what their number was, but it was pretty big. Less than 20, but more than 10. One thing that these authors did not pick up on is the final point here, that hierarchical symmetry is something that's well known in group theory, and it's embodied in a concept called the wreath product. The wreath product is more extensive than hierarchical symmetry because with hierarchical symmetry, we have to have either total or partial symmetry at each level. The wreath product allows us to have strong symmetries and allows us to mix and match symmetries at each level. How much is known about wreath product symmetry? Nearly as I can determine, beyond hierarchical symmetry as described in the papers, absolutely nothing is known about it. All right, so this is someplace where we could actually find out some new stuff by digging around. Anti-symmetry. This is very interesting. When I do comparisons, such as comparing F sub 01 to F sub 10, looking for ordinary symmetry, I could rewrite this comparison as the exclusive OR of the two cofactors, 0, 1 and 1, 0. And if they're equal, the exclusive OR has to be equal to the constant 0 function. What if we changed it so we had the exclusive OR being equal to the constant 1 function? This would give us something known as anti-symmetry. It's also been called skew symmetry. Everything's been called skew symmetry, or negative symmetry. Anti-symmetry is the most appropriate name for it for reasons that we'll give later on. I've actually incorporated anti-symmetry into the conjugate symmetry simulator. And for some circuits, it's very beneficial. For others, we found so many symmetries already that anti-symmetry doesn't add anything. If I were to use anti-symmetry by itself without looking for other symmetries, it would probably be very useful for most circuits. Okay. Kronecker symmetries. So We've gotten used to the idea that that we're going to use these relations or equations, f sub 0, 1, XOR F1, 0. And I can do this with all 6 of my comparisons, not just the one that I've pictured here. And I can set it equal to the constant 1 function. What if I use more than 2 cofactors on the left? This gives us something known as Kronecker symmetries, and there are 5 of them. The first 4 include 3 cofactors, leaving out 1. I think I've done that correctly here. If I haven't, then fix it in your notes. And the 5th includes all 4 cofactors. Nobody's really sure whether this is useful. I have 2 results looking for Kronecker symmetries. One that says that they don't hardly exist at all, and the other which says they're the most common symmetry there is. What's the difference between the 2 studies? If I look for other symmetries first, there won't be any Kronecker symmetries left. There might be a few for some circuits, but not many, hardly any. If I look for Kronecker symmetries without looking for other symmetries first, then you will find many, many, many of them under those circumstances. So they exist, but they essentially get wiped out by finding other symmetries, at least in the examples that I've used. Nobody's, as far as I know, has ever said why this sort of thing would be useful. The genesis of this is very peculiar indeed. You can look at it. If you don't understand it, just skip it. Autosymmetry. Now, this is actually an offshoot of some other research that's very, very interesting that essentially uses matrices to simplify functions. We may get into that later, but not as part of talking about symmetry. But for autosymmetry, we do kind of need to talk about that. In some cases, an n-input function can be transformed to have fewer input variables, fewer than n input variables. What we do is we form linear combinations of the original variables, and we end up with fewer than n linear combinations, and I can use these linear combinations to compute the original function. That's essentially what all this verbiage says. This is called autosymmetry, and it's rare because there has to be some sort of redundancy in the circuit for it to occur, but I understand anyway that it does occur in the ISCAT benchmarks. The way it's handled is, the way you create something like this is you compose a function with a singular matrix. Essentially what you do when you want to detect this and handle it in a circuit is you'll take a function and you'll factor out the singular matrix. Now, this is opposed to using non-singular matrices that we did in conjugate symmetry. Here I'm using only singular matrices. And it's the fact that the matrix is singular that means that that's what enables me to reduce the number of inputs to the function. Of course, I have to compute the linear combinations. I must point out at this point that a linear combination is just the sum of variables and their complements, because the only coefficients you can have are 0 and 1. Exotic symmetry. We use conjugate symmetry by using non-standard faithful representations of the symmetric group S sub n. These faithful representations are conjugate to the standard representation, which makes us want to ask the question, at least it should, are there faithful representations of S sub n that are not conjugate to the standard representation? And the answer is yes. For 4x4 matrices, there are 8 additional conjugacy classes of faithful representations of S4. For 5x5 matrices, there are 4 conjugacy classes, and I've investigated 6x6s to some degree, and there are obviously a large number of conjugacy classes there. General formula is yet to be found, so we can't really say anything about S sub n, except I do know that these exotic symmetries exist for all n. I mean, that can be shown. All right, and so we can use these faithful representations to define new symmetries. If I have a new conjugacy class of faithful representations, it defines new total symmetry, new partial symmetry, new strong symmetry, and new conjugate symmetry, to say nothing of the other types of symmetries that we've talked about. So essentially, it's a whole new universe of symmetry. And as I said, for 4x4 matrices, there are 8 additional conjugacy classes in addition to the faithful representation. And for 5x5, there are only 4. Hypersymmetry. I was sort of scraping the bottom of the barrel looking for names that go beyond symmetry. Are there groups of n by n matrices that can serve as a symmetry group of a function that do not fall into the conjugacy classes of any faithful representation? The answer is yes. Other than the existence of these groups, little is known about them or the symmetries they generate. And supersymmetry. Supersymmetry works like this. We know that the group of all 4x4 matrices, non-singular matrices that is, contains many faithful representations of F sub 4. It also contains many faithful representations of both S sub 5 and S sub 6. There are 2 different conjugacy classes of S sub 5 representations. And it's easy to show that for every n greater than 2, the set of n by n non-singular matrices contains a faithful representation of S sub n plus 1. So for 5x5s, there's a representation of S sub 6. For 6x6s, there's a representation of S sub 7, and so on. If n is even, it's also been shown that the set of matrices also contains a faithful representation of S sub n plus 2. And this would be a conjugacy class of representations, not just one. I wrote a paper on supersymmetry, a couple of different conjugacy classes of supersymmetry. There are others that I didn't talk about. And it's not really clear what it's good for, but I did show how to, what it was and how to detect it. A lot of questions still remain to be answered here. And now for yet another type of symmetry. I haven't figured out a name for this yet, but when we consider relations of the form F01 XOR F10 is equal to the 0 function or equal to the 1 function, is it possible to use some other function on the right other than constant 0 and constant 1? Done a little poking around with this, and my answer to this is probably yes. But other than that, nothing is known about it. These are all the types of symmetry I could think of. I imagine that, other people could think up other things too, but this is a lot of stuff. And here is the upshot of this. Do we know how to detect all of these different types of symmetry? Yes, we do. That problem has been solved, and I'll show you tomorrow how that's done. What are these types of symmetry good for? Well, we haven't exactly solved that problem. Sometimes we know, sometimes we don't. And that's just the way it is. We'll talk to you about detecting symmetries